Hi everyone, welcome back. Now we are going to hear the talk or else an exploration of obscure control flow. Please give a warm welcome to Amethyst Reese.
Hi, folks. I know we're in the final talk slot of the day, and you could be off getting food already, but for some reason you chose to be here. I'm sorry. So I need to start with a content warning. I don't know how else to say this, but it's going to show code. Lots of code. And I'm going to try to move quick. Most of the code will be small snippets. Large fonts, though, so it should be easy to read and follow. But don't worry about catching key moments with your phone. I'll share a URL at the end. That'll include everything, the code, the slides, my entire script. So I was planning to give you all an ultimatum to go with this talk title, but I think we've had enough threats with the world lately. It's kind of hard to imagine a punishment worse than what's already going on, so I'm going to try and ignore all that for now. We'll have fun with the topic. So what do we mean by control flow? This refers to any part of our code that tells Python runtime how to alter the flow of execution from one line of code to the next. Hopefully you're already familiar with the fundamental basic blocks of control flow. That's conditionals, loops, and functions. Every other form of control flow can be expressed as a combination of one or more of these basic mechanisms. And of course, Python has many more higher level types of control flow, and all of them are defined as part of the language grammar. We can even look at Python's grammar specification, and we can see all the possibilities. Did you catch all that? Because it's a bit much. Now obviously that's a lot, and thankfully for you, I'm not here to teach you about the language grammar. And I'm assuming everybody's familiar with the basic control flow, so let's look at the less obvious options that Python gives us to manage the flow in our projects. So comprehensions are relatively unique to Python among mainstream programming languages. At their core, they're just syntactic sugar around for loops and if blocks, and the primary purpose is to build collections of data. Now, ignoring performance, these two pieces of code will produce identical results, but the key difference is in readability. Now, slightly ironically, opinions on which is more readable will actually vary depending on the engineer and their familiarity with Python or other languages. As we make the comprehension more complicated, we should consider the benefits and trade-offs of the performance and compactness against the readability and maintainability of the code in question. I don't think many would argue against using a comprehension for simple operations like this. But what about now? Here we're adding a second for loop to the comprehension, but because of the way that they work, we're forced to order the clauses out of contextual order, and this obfuscates the intention of the code. Some manual reformatting can help, and I do think this improves readability, but at this point it's becoming harder to argue which of these two methods is easier to read and understand. And where do we draw the line? Well, one thing to consider is that multi-line comprehensions like this hide away the inherent cyclomatic complexity of the code. It's a single comprehension, of course, so it must be fast, right? Whereas the traditional form of the code requires multiple levels of nesting, making it much more obvious to the reader that this will likely result in slow performance on large data sets. And really this means our choices as developers impact code readability and thereby impact the maintainability and reliability of our software. We must weigh the advantages and disadvantages of various approaches and consider not just the performance of our code, but our confidence that future changes won't cause bugs, or even just the cost and time and experience needed to understand and modify our code after it's already been shipped to production. We need to consider what the right choices and trade-offs are when we're writing their code. So with that said, let's look at some of the less obvious parts of the language and see if we can't find ways to improve readability of our code in the process. In particular, let's look at the else block. Mostly known for its use as part of an if statement, but it can be paired with other code blocks as well, like exception handling, where we can use the else block for some common code patterns. As many of you are likely aware, adding a finally block to try except gives us a way to run some code afterwards, regardless of whether an exception was raised or not. By comparison, the else block is only run if there was no exception raised. We can think of this like setting a success variable and then checking that value later, either in a finally block or outside of the try except entirely. And I'm sure many of us have seen or written code patterns like this before, but maybe that code should have just been an else block. Python gives us that logic for free, and it's fewer lines of code in the process. And this helps us maintain the best practice of minimizing the amount of code that's inside the try block itself, while also minimizing the effort we need to track whether or not our code was successful. But we do need to beware. Unlike finally, a return statement here will not execute the else block. So we either need to keep the return outside of the try block, or we need to be sure that our critical code remains in the finally block instead. Now we can also use the else block in for loops, somewhat analogous to its use with try except. Here the else block is executed if and only if the for loop exhausts its iterable. But if the loop reaches a break statement, then the else block is skipped. So you can think of this similar to try except else, but instead of executing if no exceptions are raised, it executes if no breaks are raised. So we can imagine this code pattern. We're iterating over some data, and we break on the first time that we find a match. Now, instead of maintaining new variables to handle a case with no match, we can replace that logic with an else block, simplifying our code, and hopefully making it more readable and maintainable in the process. The last use case here is the while loop. Similar to the for loops, the else block here executes if no break statement was reached. But we can also think of it in a different way, or better way. The else block runs when the condition of the loop variable evaluates as false. Functionally, it's equivalent to an infinite while loop, where you nest an if-else block instead and break out of the loop once that condition is false. But again, once a break statement is reached, the loop condition won't be reevaluated and the else block will not be executed. Now, we're going to jump down the rabbit hole a bit. Let's look at the ways we can use or abuse some of the tools that Python gives us. Things that we might not think of as control flow. Like decorators. The fun little things that we tack onto our functions and methods and classes. And some of the best inventions in Python have come out of decorators, like data classes. But really, decorators are just callable objects, and that use syntactic sugar from the language. Adding the @decorator above our function is shorthand for calling the decorator, passing it our function, and then overriding that function with whatever the decorator returns. Making a decorator is simple as making a function, only this function takes a function or a class as an argument, does something with it, and then returns the new object when finished. Most common decorators are function wrappers. They define an inner function wrapping the original one, do something interesting, and then call the original and return the results up the stack. This might be something as simple as logging every time a function is called. And this allows our greet function to then add the log calls decorator, and now every time we call greet, we automatically get logging output, including the name of the function that was called and the arguments it was called with. But what makes a decorator control flow is key. Using the @decorator syntax is literally calling and executing the decorator's code at the moment that the function it's wrapping is defined in scope. This means that our decorator will execute before the function it's wrapping is ever used, and if we import this code, we'll see that before we ever even call the outer function, the decorator has printed its message, at import time no less. And when we do call the outer function, the decorator runs again to process the inner function, even though it's never called or used. But decorators don't have to return functions, or methods, or classes, or callable. They don't even need to return anything at all. All that matters is that using the syntax implicitly calls your decorator function. Now, a quick side note. One of the first programming languages I learned as a kid was Perl. It has a few variants of loops that invert the expected conditions of the loop expression. The until loop is the inverse of the while loop, and it will repeat the body of the loop until the expression evaluates true, rather than looping until it's false. I think that's kind of neat. So I made it in Python. We just do this as a decorator. In its most simple form, it takes a callable as the loop predicate and calls the wrapped function repeatedly until the predicate evaluates true. But this decorator doesn't return a new function waiting to be called. It just starts running it immediately on definition. And this lets us write until loops in Python. The loop body will be called until the predicate, the lambda, is true. And yes, it's a little bit ugly, and we have to take care to use non-local state to persist data between iterations. And all of this is just to satisfy some nostalgia and avoid a negation in the loop condition. But it's a glimpse into what we can do with decorators. So we can go deeper. Perl also has this gem. It's familiar to many C programmers. This is a do-while loop, and it always executes the body of the loop at least once, and then it evaluates the loop condition before repeating. In certain cases, this is helpful because it reduces duplication of setup code, but Python has no native syntax for doing this. And 22 years ago, PEP 3.15 was proposed with new syntax to add a do-while loop to Python. This was for Python 2.5. I rediscovered this while writing the talk, and I think it's finally time that we do justice for PEP 3.15. So I'm announcing the public release of the do-while package on PyPI, already available. Yes, I did this for the bit. So let's see it in action. This new package lets us finally write a do-while loop in Python, with the @do decorator wrapping the body of the loop, followed by a call to the while function with the appropriate predicate. This predicate also prints the value so we can confirm when it's actually being evaluated. And when we run the code, we can confirm that it's evaluated after the first iteration, thus ensuring the body is always run at least once, even if the predicate was always false. How does it work? Well, it's quite simple. The real package on PyPI has a little bit more to it, but it can be boiled down to this fragment. The do decorator function doesn't return anything, and then it just creates and saves a wrapper and waits for the while function to be called. Only then does that wrapper execute using the provided predicate to control the loop. Now the release version also supports collections or other truthy objects as predicate, running the loop until those objects become falsy. This lets us clean up some uses of global or non-local, and we can get by without a lambda for the predicate. I think this is about as nice of a do-while loop as we can get, without modifying the Python runtime itself, of course. And again, we can see that the loop is working as we expect, with all of its post-evaluation glory. So, great success. But I get it. Let's climb back out of the rabbit hole. Decorators are passe. What we really want is control flow that we can use for good, not evil. Something like generators. So generators are a special type of function that can pause execution, yield arbitrary values, and then resume from where they left off again. Writing any function with the yield keyword automatically turns it into a generator, and when reaching a yield statement, the runtime will pause execution of that function and pass that value back to whatever is consuming the generator. We can also use yield from, which will again pause our function, but now it will defer to an arbitrary iterable instead, yielding each of those values until it's exhausted, and only then resume our function afterwards. But unlike normal functions, when we call a generator function, it doesn't immediately start running. Instead, we get a generator object, and we need to do something with that object to make it start running and yield those values. Now, these generator objects are themselves iterable, so the easiest thing to do is to just loop over them. For each iteration of the loop, it runs the generator until it either yields value or finishes. And once the generator yields a value, we can do anything we want in the body of the loop with that value. Alternately, we can call next on the generator object to run it until it yields a value. And again, we're free to run arbitrary code and do anything until we want to call next again and resume the generator. But perhaps unexpectedly, we can actually send data back in to a running generator, in between the yielded values that we've received from it. However, we need to stop treating generators like normal iterators and loops. We can do this by calling the send method on a generator object. The value we pass will be sent into the generator function will run until it yields again, and that yielded value will be returned to us from the send method. On the function side, values sent into the generator are presented as the return value of the yield statement itself. And remember that when we first call a generator object, the function hasn't started executing, so there's no current yield statement to receive a value. This does mean that the first time that we call the send method, we have to send none. This is actually what starts the execution of the generator function, so that it can start yielding its values. Now, if the generator raises an exception, that exception is also raised from the send method, and we can catch and handle that exception. But like sending values back into the generator, we can also inject exceptions into the generator. The throw method will raise the given exception inside of the generator function where it was previously executing, triggering the normal exception handling process. But do beware, if the generator doesn't actually catch that exception, it will be raised right back out from our throw method. Otherwise, if it handles it correctly, then we'll get the next yielded value in return. And lastly, when a generator function returns or finishes executing, it will raise a stop iteration exception, just like any other iterable. We see that exception raised when we call send enough times to reach the return statement, and the value from the generator's return statement is available as a property on the exception object. We can use that return value however we want. Altogether, this gives us bidirectional communication between generators and the code wrapping them. This forms the foundation for concurrent interleaved execution of two or more functions, commonly known as coroutines. Now, async IO itself was originally built on top of generators, with event loops that round-robin execution between multiple active coroutines. But that's a different rabbit hole for a different day, and I already gave that talk back in 2019. So what else can we do with this knowledge? I'm sure many of you are familiar with, or have at least seen the zip function before. It takes one or more iterables and produces tuples combining the values from each step of each of those iterables. We can build a version specifically for generators. Our version of zip can be relatively simple. We take any number of generators, call send on all of them, and yield a tuple with the values gathered from each of those generators. We repeat that until one of the generators finishes and raises a stop iteration exception. At that point, we clean up any unfinished generators by calling close on all of them, ensuring that each generator has the chance to cleanly exit. We can use that with our toy generator function here and see that it generates tuples accordingly and also stops correctly once the shortest generator is finished. Not really groundbreaking or exciting though. So let's try to think outside the box. We know how to start generators. We can switch execution between multiple generators at the same time. So what about a state machine? We could have each state be a separate generator function and use the yield statement to transition from one state to another. We can even build a bare-bones state machine in a single function. Given a starting state, we initialize generator functions as needed, running the current state until it yields a new one, and then we repeat. And we could also implement message passing between states, but we don't need that yet. This lets us write simple implementations for each state as individual generator functions that simply yield the name of another function to transition to. And when we transition back to an active state, it continues running exactly where it left off. So if we run this state machine from the state 1, we can see that it transitions to each new state, coming back around to the first one and resuming its execution, and then eventually our program ends once a function returns without yielding a new transition. But we can do something fun with this. I'd like to introduce the great Python control flow text adventure. Now, text adventures were some of the earliest PC games ever made, and most of them are just a collection of rooms and actions combined into one giant state machine. Perfect for a toy project. We can build a simple text adventure using our generator state machine with a few small changes. Each room can be its own state. We can use a shared game object to keep track of data across rooms, and the logic within a room's function can interact with the user, change the game state, or yield a different function in order to transition the player from one room to the next. So let's play our game. If you have UV installed, you can play along from your own machine with this command. The URL simply redirects to the latest version on my GitHub repo. Is this big enough for everybody to read it? Nope, it needs to be bigger. All right, welcome to the text adventure. You wake up in a bedroom and you feel tired. Do you want to go east or sleep? What a week. You wake up in a bedroom. Do you want to go east or sleep? A little nap can't hurt. All right, let's go east. All right, you're in a hallway. Do you want to go north, south, or west back to the bedroom? Sorry, I don't have too many interactions. You're in the living room. North, south, east, or west? I heard west first. You find yourself in a closet. It's dark. Pull the chain, but the bulb is burned out. Let's go back to the living room. You're in the kitchen. There's cake. You eat the cake. It has strawberry filling. Sleep. Sorry, not an option in the living room. All right. You walk out the front door, and it's a great day to be in Pittsburgh. All right, thank you for playing along. You're great. Now, for those wondering, the full game engine here, if you want to call it that, weighs in at a hefty 28 lines of code, maybe about double that if you include the doc strings and white space. But the entire file, including all of the rooms and the logic and the generator functions and everything, is a little under 200 lines total, so not that bad. All right, we're running out of time, so where do we go from here? Well, if there's one lesson, it's that you should always try to write obvious code. Clear is better than clever. Everyone who has to read your code in the future, including yourself, will appreciate obvious code. Now, often this takes more time than just writing code that works the first time. But often, I would encourage you to take that time. Think about the ways that you can use or abuse your language to make your code more obvious. Make the important code clear and concise and bulletproof. Just maybe don't jump the shark. Think twice before writing your loops with decorators. And above all else, have some compassion for your coworkers, but also for your future self. And as promised, the slides and example code, including the text adventure game, they're available on my GitHub repo. This includes all of my past talks as well, so if you really do want to dive into Python grammar, syntax trees, or the nerdy details of coroutines and async IO, there's something here for you. And thank you all for sticking around. Appreciate it.